Okay, hello everyone. I'm Tanmay Inamdar and I'm presenting our work titled FPT Approximations for Connected Maximum Coverage. This is a joint work with Satyabrata Jana, Madhumita Kundu, Daniel Lokshtanov, Saket Saurabh, and Meirav Zehavi. So let's start with a little bit of background on coverage problems. So so coverage problems are widely studied in combinatorial optimization, approximation algorithms, and so on. And the basic setup is as follows. So typically we are given a finite set of n elements, which is called a universe. And we are also given a family F, which consists of different subsets of the universe. And basically, we want to cover some elements of the universe, right? So, for example, in the set cover problem, we want to find the minimum number of sets that will cover the entirety of universe. In the hitting set, the roles are reversed. So actually, we want to find the minimum number of elements now to hit all the sets in the given family. In the max coverage, the objective function is different. So you have a strict budget of k sets, and you want to choose these k sets in a such a way so that it maximizes the number of elements that you cover. You can also have vertex cover, which is like a special case where you have a simple undirected graph and you want to find the minimum number of vertices to cover all the edges. You could also have a partial version of vertex cover where you don't want to necessarily cover all the edges, but you want to cover at least t edges using the minimum number of vertices. You can have dominating set where vertices cover adjacent vertices and so on and so forth. So all of these problems are extremely well studied in classical approximations. So let me uh, give you like one generic problem which can encompass all of these problems in a unified fashion. So this is called a red-blue dominating set problem. So here we have a bipartite graph. On the one side, we have red vertices. On the other side, you have blue vertices. And you have edges between them. And the question is as follows. So this problem is called partial red-blue dominating set. So the input is this graph, and there are two integers k and t. And the question is, are there k red vertices which come from the left-hand side that will dominate at least t blue vertices from the right-hand side? Right. So this is the decision version of the problem. But if you think about optimization version, which is what typically we are interested in approximation, then there are two natural versions that you can come up with. In the one version, you kind of fix this demand of dominating at least t blue vertices, but you want to minimize how many red vertices you choose. So the approximation will be on the solution size. On the other hand, you can fix the budget of red vertices that you are allowed to pick, and then you want to maximize how many blue vertices you dominate. So that would be the maximization version, right? And as I said, this generic problem can capture all of these problems that I mentioned earlier, including max coverage, set cover, hitting set, dominating set, and so on and so forth. Right? Okay. So, because there are two natural optimization variants, it is more convenient to talk about an alpha beta approximation algorithm. So, this alpha approximation algorithm, either it will find a set of at most alpha k red vertices that will dominate at least beta t blue vertices, or it will correctly output that there is actually no subset of k red vertices that can dominate at least T blue vertices. So this is a typo. It should be at least T blue vertices, not beta. Okay. So here alpha is at least one and beta is between 0 and 1. So for that, you can define an alpha beta approximation algorithm, which can talk about both maximization and minimization versions in a single unified fashion. So, because this partial RBDS problem generalizes set cover, Actually the well-known log n approximation for set cover that translates to an order log n comma 1 approximation algorithm, and similarly the greedy algorithm for max coverage that translates to a 1 comma 1 minus 1 minus 1 by e approximation for the partial RBDS problem. These are polynomial time algorithms, and we also know that these bounds are tight. So unless p is equal to np, you cannot improve significantly on each of them in general. And in fact, these approximations are tight even if you allow running time, which is fixed parameter tractable, parameterized by the solution size. So you cannot beat 1 minus 1 by e for domination of t blue vertices. Here, you cannot actually get any approximation factor which only depends on k. Okay, so I'm not defining these things formally, but the point is that the polynomial time approximations are also the best approximations even in FPT time. But this is for general set systems where you do not impose any restrictions on the set family or the bipartite graph. But if you do assume some special properties of this graph, then you can do much better, especially in FPT time. So um, either if you want to approximate the number of blue dominated vertices, or if you want to approximate the size of the solution, in either case you can get a 1 minus epsilon or 1 plus epsilon approximation as appropriate, if you allow for FPT running time in k and epsilon, as well as some other parameter which depends on the structure of this graph, right? So these results are relatively recent, and they show that you can actually do much better in FPT time, given certain special properties about the underlying set system. So, but in the classical polynomial time world, people have gone beyond the classical vanilla coverage, and they have also studied coverage in addition with certain constraints. For example, capacity constraints or fairness constraints, and for which is the focus of this talk, connectivity constraints as well. So so in Soda 24, Kuller et al. Defined connected versions of dominating set. Actually, they studied two versions. So in the partial version, so basically you are given a graph, and in the partial version, you want to find the minimum number of connected vertex subset that can dominate at least t vertices of the graph. And for that, they designed an order log delta approximation where delta is the maximum degree of the undirected graph. And in the budgeted version, you want a case-sized connected vertex subset, and you want to dominate as many vertices as possible. And for this, they designed a constant factor approximation. This was for in the special case where you have a graph. Relatively more recently, Hogbaum and Rao, and also D'Angelo and Delfaras, they studied a connected version of max coverage where you have an underlying set system given by universe and family, and you have a unrelated graph defined on the universe, and you want to find um, you have a undirected graph defined on the subsets of this family, and you want to select k sets from the family, which on the one hand, they should form a connected subgraph of this connectivity graph, and they should cover the maximum number of elements. And for this, these two papers designed polynomial time approximations, but the approximation guarantees, they were kind of a sub constant. So because this is a maximization problem, the approximation ratios were little of one, which depend on the connectivity graph structure. Okay, so again, we want to generalize our model of red blue dominating set so that we can capture all of these connectivity constraint problems as well. And for that, remember that we had this bipartite graph defined on these red and blue sides. So that graph we call GCOV because the coverage is going to come from this graph. But you also consider another graph which we call GCON for connectivity. And this is like a unrelated graph which is only defined on these red vertices. And the connectivity requirement comes from this graph. So the solution should form a connected induced subgraph of this G connectivity graph, and it should dominate certain number of blue vertices. So for example, if you look at these two vertices, these two red vertices here, they don't form a feasible solution because they don't form a connected subgraph of GCon. But if you include this third vertex, then it forms a connected subgraph, and then it is going to dominate a certain number of blue vertices. So that is the problem that we consider in this paper. So it is called partial connected red-blue dominating set, or PCRBDS. I know it's a mouthful and the setup also requires some time to understand. So let's go over it. So in the input, we are given this red-blue bipartite graph, which is called GCOV. So here on the one side, you have these red vertices. On the other, you have these blue vertices. And you have a separate unrelated graph which is called GCon, and that is only defined on these red vertices. Okay, and then you have these two integers k and t, where k is the size of the solution and t is how many blue vertices you want to dominate. So the question is the same: is there a subset of size at most k of red vertices? So that on the one hand, if you look at the induced subgraph of GCon, then the solution forms a connected subgraph, and at the same time, it should dominate at least T blue vertices in the coverage graph. So that's the question. And one thing to notice here is that this partial connected red-blue dominating set immediately generalizes the non-connected version, the normal red-blue dominating set, because you can just define the GCon graph as a clique on these red vertices, right? So basically, when you define GCon as a clique, then every subset of R induces a connected subgraph, which basically makes the first constraint redundant, and then you just want to dominate at least T blue vertices, which was the original problem, right? And here also you can notice that we have two natural parameters to optimize, the solution size as well as how many blue vertices you dominate. So again, uh, that gives rise to two different optimization variants. And I'm not going to go into the details, but this problem actually generalizes all of these problems which were studied in the literature. For example, connected max coverage, connected hitting set, connected dominating set, connected partial dominating set, so on and so forth. Right. So this is the problem that we have defined. And because again we have two different optimization variants to consider, again let's extend this notion of alpha beta approximation to our model, where uh, this alpha beta approximation algorithm, it's either going to correctly output that there is no subset of k red vertices that can dominate t blue vertices in the coverage graph, and it induces a connected subgraph of the GCon graph, or it will output a subset of alpha k red vertices that can dominate beta t blue vertices in the coverage graph, and also it induces a connected subgraph of GCon, right? So we will be looking at these kind of alpha beta approximation algorithms. So again, because this connected version generalizes the non-connectivity constraint version, it inherits all these hardness results from that. So for example, we know that it is W2 hard parameterized by K, even when the graph, the connectivity graph is a clique. And there are no non-trivial approximation algorithms parameterized by K. So FPT does not give us any more power. On the other hand, we saw some positive results in polynomial time on the earlier slide. So the natural questions to ask is, because it is already W2 hard parameterized by K, is it actually FPT if you parameterize by T, the number of blue vertices which you want to dominate? So that's the first question. The second question is, if you So these hardness results are when you do not assume any structure on the coverage graph, but can you actually get better approximation algorithms if you do assume that your coverage graph satisfies certain properties? And similarly, for approximating the blue vertices dominated, you can get a 1 minus. So there was like a constant factor approximation in the graphs, but can you get any non-trivial approximation algorithm for approximating t again when you assume some structure on the coverage graph? Okay, so for question number one, we are not assuming anything about the structure of coverage graph, whereas for the next two questions, we do want to put some restrictions on the coverage graph, right? And all of these questions are actually inspired from the non-connectivity constrained red-blue dominating set problem, where the answer to all of these three questions is yes. So the normal partial red-blue dominating set, where you don't have any connectivity constraint, that is FPT parameterized by T. There is actually a additive approximation for solution size if you assume certain restrictions on the coverage graph. And similarly, for approximating t, you can get a 1 minus epsilon approximation in FPT time, again, when you assume certain restrictions on the coverage graph. So now we want to ask the question, do these results also extend to the connectivity constraint coverage? And notice that for question number two and three, we are not putting any restriction on the connectivity graph. So that can be completely arbitrary graph on the red vertices. We are just assuming certain structure on the coverage graph. Okay, so what are our results? I have been saying that we want to assume some restriction on the coverage graph. And the restriction that we are going to assume is that this graph is KDD free. So KDD refers to the complete biclique on D vertices. So you have D vertices on one side, D vertices on the other side, and you have all the D square edges. So this bipartite graph is not present in our G curve as a subgraph, right? So that's the structural assumption that we are making. And at first, this might seem like an arbitrary restriction, but this is in fact a very common restriction to impose in parameterized complexity. And the reason is that the family of KDD-free graphs, it actually generalizes a lot of well-behaved graph families. For example, planar graphs, bounded genus graphs, bounded tree width graphs, H minor free graphs, and more generally bounded degeneracy graphs. All of these are uh, content in the family of KDD free graphs for some D, right? So that's the reason why we impose this KDD free condition. So these are our results. So to answer the first question, the partial connected red-blue dominating set problem, we show that it is solvable in 2e to the power t plus little of t times polynomial running time. So it is FPT parameterized by the number of blue vertices that you want to dominate. And for this first result, we do not impose any restriction on the coverage graph as well as connectivity graph. So both of these graphs can be completely arbitrary. For the next two results, as I said, we assume that our coverage graph is KDD free, whereas the connectivity graph can be completely arbitrary. So here, if you want to approximate T, the number of blue vertices that you dominate, then you can get an approximation scheme. And the running time of this approximation scheme is 2 to the order k square d over epsilon times polynomial. So notice here that the degree of the polynomial, the power of n is just a constant. It does not depend on k, d, or epsilon. So that's the result for approximating t. Whereas for approximating the solution size k, you can get again an approximation scheme. So you can get 1 plus epsilon approximation for size. But then the running time is 2 to the order some poly in k and d times n to the order 1 over epsilon. So here the dependence on epsilon is like a p-task. So this approximation scheme is called efficient fixed parameter approximation scheme, or EPAS, whereas this type of running time where the dependence on epsilon is n to the power some function of epsilon. This is called parameterized approximation scheme or a PAS. So in this talk, I will just give a brief intuitive explanation of this result, and then the other results can be found in the paper. So, so what is the intuition behind approximating T? So the first intuition is that imagine a solution of size k which dominates at least t vertices and it forms a connected subgraph of gcon. And imagine for a moment that suppose you look at different vertices of this solution, they don't like no pair of red vertices in the solution share a lot of blue common neighbors. So there is negligible amount of overlap in terms of blue coverage. Then basically the coverage function, which is usually submodular, it more or less behaves like additive in terms of the blue degree. So you can simply add the blue degree rather than kind of worrying about overcounting. And if we were in this ideal scenario, then we could just set the weight of every vertex as the number of blue vertices that it sees or its blue degree. And using these weights, we want to find now a k-sized connected subgraph of our connectivity graph gcon, which has the maximum possible weight, where you just add up the weights. And this problem you can solve in 2 to the power order k into poly n time by pretty much standard tools in parameterized complexity. Okay, so k-sized connected subgraph of maximum weight can be found in FPT time. But in general, the wishful thinking that we were doing, where coverage behaves more or less additively, that assumption might not be true. So there can be a lot of overlap in different vertices of the solution, which will make the coverage not behave like an additive function, and that can kind of mess up with this strategy. So the idea is to somehow exploit the fact that our coverage graph is KDD free, which means that it is sparse in some quantifiable way. And we want to use that to somehow handle the high coverage overlap using the power of FPT time, so that ultimately we can reduce it to this max weight connected subgraph problem, which then you can solve in FPT time. Right. So this is the intuition behind our algorithm. Now, let me just briefly explain the steps of our algorithm. So the first step is to construct what we call the conflict graph on the red vertices. So this is an auxiliary graph which we use in our algorithm. And here the vertex set is red, and the edges between different red vertices indicate that these two vertices have a lot of blue overlap in terms of coverage. Okay, so basically, if you have an edge between two red vertices u and v, then you cannot simply add the degree of u and degree of v, because there can be a lot of overcounting, which is precisely what we want to avoid, right? So then what we show is that if our coverage graph is KDD free, then this conflict graph will have maximum degree, which is bounded by a function of k, d, and epsilon, right? So I'm not precisely defining how this conflict graph, like what is the threshold for high coverage overlap, but this bounded degreeness comes from that definition. Okay, so in any case, the maximum degree of this conflict graph is bounded by some function of k, d, and epsilon. So then we use some tools from parameterized complexity to identify some disjoint induced subgraphs of the conflict graph. So we call this collection calligraphic C, so that if you have a solution S, and if you look at that solution induced in this conflict graph, then it suppose breaks down into L different connected components, C1, C2 up to CL. Then these connected components are part of our collection that we are going to find. Okay, so we are going to find a superset of connected components of our solution, which we don't know. So the task is now to somehow reach to these connected components or some approximation of those components. Next, So we have this collection C in our hand, but we don't know which L components together are going to give us the solution. But still, we will look at this collection C and we will use it to sparsify our coverage graph. So now, if you look at two different vertices which belong to the same connected component, then it means that somehow they have a lot of coverage overlap in terms of their blue degree, right? But anyway, we know that either a connected component should fully belong to a solution or it should not belong to the solution at all because of this property. So using that property, we are going to somehow delete some edges from our coverage graph. And that will ensure that we will somehow reduce the double counting which is going on, which was somehow the problematic case. And once we sparsify our coverage graph, that will transform our coverage graph to becoming more or less additive in this sparsified version, which we call G-spar, right? And now we use this sparsified graph to define weights as we did before, and finally reduce it to finding a maximum weight K size subgraph in our connectivity graph. And again, if all of these steps go through, then this last step, we can use FPT running time algorithm to find a solution if it exists. Of course, this step number 4 is not exact. So here, coverage is not exactly additive. It is approximately additive, and this is where we lose an epsilon factor in the coverage, right? And that is how we get 1 minus epsilon approximation for blue domination, for approximating blue domination in running time, which is FPT in K, D, and epsilon, where we assume that our coverage graph is KDDP. So hopefully it gives you some ideas about our approximation algorithms. That's the end of my presentation, and thank you.